inspired academics, professors like me and many others, because of his uncompromising views on research and science and aiming for big questions, real big questions, research for scientific truth. He's also inspired many companies, including Google, to do groundbreaking research and to aim high for big goals. And so he really he's one of those few people that can stand here and one can say unequivocally that he has inspired millions of people. And it's not every day you meet someone like that. And if you haven't been inspired by him, watch this talk.
Well, thanks for the introduction, Nando. After that, it can only be a disappointment. This is a talk that I prepared to give to ICAS, which is in Vancouver, and they persuaded me to come and give it again here. So it contains some fairly sort of basic stuff about deep neural nets that some of you will know very well, but others of you hopefully can benefit from. I'm going to talk a little bit about the history of neural network research, particularly nets with lots of layers of features, and very briefly about how they're used in speech systems now. I'm going to talk about how we then extended that work to make them work for object recognition, and some of the tricks required to get things that were really good at object recognition. And I'll talk about a couple of other successes of deep neural nets. And then I'll end with some speculation about future speech recognition systems, which I think will be very different from current ones. So, if you want to recognize patterns, it's obvious how to do it. You get some features from the image or whatever the input is, and then you learn what weights to associate with the features to decide which class it is. And that's called pattern recognition, or statistical pattern recognition. And the sort of issues are, where do the features come from? So one thing you can do is you can hand engineer features. And people have done a lot of that. Another thing you could do is you could say, I'm going to have a way of defining a feature by saying, I'll take certain of the input patterns I see, and I'll have some way of measuring how similar a test case is to those inputs. And then I'll have some clever way of selecting which of the input patterns I should use, and a clever way of putting the weights on the ones that I select. And that's called a support vector machine. And this story would be a lot simpler if support vector machines had really been invented before backpropagation, because that's the natural order of things. Unfortunately, we invented backpropagation too soon, but let's suppose we invented it after support vector machines. The story would be nicer. And the last method, of course, is to learn what the features should be. So in the mid-80s, actually in the 70s, Paul Werbus came up with the backpropagation algorithm, but didn't manage to convince anybody. And then in the mid-80s, several people developed it, including Jan LeCun and David Grommelhart and Neil Ron Williams. And backpropagation works by saying, we'll have a feed-forward neural network, and we'll compare what comes out of the network when we give it, say, an image to classify with what we want to get. We'll take some measure of the discrepancy. We'll send that backwards through the network, and we'll use the chain rules so that we can compute for every weight in the network how changing that weight would change the discrepancy with the correct answer. And then we'll just update the weights a little bit in the direction that reduces the discrepancy. And so that's called stochastic online gradient descent. And it turns out it's a very sort of primitive optimization method. And for very big data sets, it works better than any of the fancy optimization methods we've been able to find, with a few tweaks. And so we were very excited about backpropagation because we thought we finally solved the problem of where features come from. You just have a multi-layer neural net and you learn all the features. And we make these smooth non-linearities so we have nice derivatives. And the problem is solved. And in practice, it was a bit disappointing. So people developed a story of why backpropagation didn't work. And the story, I took this from one of my slides from a while ago, so this was the story I was telling. It doesn't work because you need too much labeled training data. And almost all the data you can get easily is unlabeled, because you have to know what the right answer is to train these nets. And you'd be much better off training a generative model that doesn't need to know the right answers. The second argument was the learning time doesn't scale well. If you have one hidden layer, it works quite well. But as soon as you have multiple hidden layers, it learns much too slowly. And then the normal thing, it can get stuck in local optima, that aren't as good as they might be. It's very hard in a high-dimensional space to figure out what's really going on. You don't know whether you're stuck in local optima until you develop a much better optimizer and discover that all the things you thought were local optima have downhill directions sloping out of them, and so they weren't local optima after all. But this story is actually nonsense. That's not what's wrong with that propagation. What's wrong with that propagation is we didn't collect enough labeled data, but the speech people did. We didn't have fast enough computers, and we didn't have a sensible way to initialize the weights. And if you fix those three problems, it works really well. So it really is the answer. At least it's the answer to where do features come from, or is there some plausible way of getting features? It's maybe not where features come from in our brains, but it will work on a computer. So since the mid-80s, we've got much bigger labeled data sets. First in speech and more recently in vision. Computers got a whole lot faster, particularly with graphics processor units. We suddenly got a factor of 30, which made a huge difference. And we found better ways to initialize the weights without using labeled data. And as a result, neural nets got to be much better at some things. In particular, they got to be better at acoustic modeling for speech recognition. So in speech recognition, you have hidden Markov models for phonemes that say this phoneme has this state, then this state, then this state. Then you have to look at the sound wave and say this bit of the sound wave could maybe be this state of this phoneme. And so you need something to associate bits of the sound wave, or coefficients you've extracted from the sound wave, with individual states of hidden Markov models. And of course you don't know for sure, so you need to take some coefficients extracted from the sound wave and say there's a probability of kind of 0.3 it's this bit of this phoneme, and 0.4 it's that bit of that phoneme, and so on. And that's what deep neural networks are now routinely used for, and they're replacing the previous method, which was Gaussian mixture models. So I'm going to talk a little bit about initializing the weights. Historically, this was very important in overcoming the belief that these deep neural networks were no good and could never be trained. And that was a very strong belief. A friend of mine sent a paper to ICML not that long ago, and the referee said it shouldn't be accepted by ICML because it was about neural networks, and that wasn't appropriate at ICML. In fact, if you look through ICML last year, there were no papers with neural in the title accepted. So ICML should not accept papers about neural networks. That was only a few years ago. One of the IEEE journals actually had an official policy, as far as we can see, of not refereeing neural network papers, just sending them back. So it was a strong belief, and not entirely without evidence in its favor. So here's how you can initialize the weights in one of these networks without needing labels. You start by learning a generative model of the structure of the input variables. And you do that using, one way to do that is to use a little kind of generative model that has input variables, and it has one layer of latent variables. It has symmetric connections, so this is really like a Markov random field that's bipartite. It doesn't have any connections among the latent variables, which makes life much easier. And it turns out the maximum likelihood training algorithm for this is quite complicated. But there's an approximation to it, a very crude approximation, called contrastive divergence that's very simple. I'm not going to go into that because I want to say how this fits into the bigger story, and I don't have time. But it turns out, given some data, there's a very simple way to train these nets, which are called restricted Boltzmann machines. It's not maximum likelihood, it's not optimal, but it's fast and it does a reasonable job. And that's good enough for our purposes. It means you can show it some pixels here, you can train it quickly, and you can get some feature detectors here that are capturing the correlations among pixels. So you'll get things like little edge detectors or corner detectors or things here. And then the real trick is, after you've done that, you can then take the vectors of activity of these hidden units and treat those as data and do it again. So now we can take this as data and learn a second layer. And you can then do it again, and so you can do it as many times as you like. And the crucial property this has is that if you train a whole stack of models like this, you can show that you can put them together into one big model, and every time you train an extra hidden layer, you'll get a different bound on the log probability of the data, and as you make the model deeper, that bound will get better. In other words, you definitely win by adding an extra hidden layer in terms of your lower bound on the log prob of the training data. So it's the right thing to do in that sense. You're making progress. Now, the proof, of course, requires various conditions, like you did maximum likelihood learning for each little restricted Boltzmann machine, and that the layers never get narrower. And so we just violate the conditions of the proof outrageously all the time. But the proof is nevertheless very important, because it shows that under certain circumstances, this business of learning a layer at a time is academically respectable. There is some band that's improving, and so it's a reasonable thing to do. It's not pure heuristic. And that proof gives you enough cover so you can get on and do the research. And not get the papers routinely rejected. So here's how we used it in speech recognizers. Each sort of green column here is a frame of coefficients you've extracted from the sound wave. And in fact, the best thing to use is just filter bank outputs. In speech, they developed more complicated things called Mercalli coefficients. But they would develop mainly to decorrelate things and to reduce dimensionality so that a dumb method called Gaussian mixture models, which is just basically smooth table lookup, could model this data. And once you use a restricted Boltzmann machine here, then you can afford to have a less processed version of the input. In other words, it can decide what features it wants to extract. And you can look at more windows of coefficients. You can look at a bigger time period. For the inputs, these are going to be real values. Later on, we're just going to use binary valued units. And so you use a special kind of Boltzmann machine for the inputs, which is called a Gaussian restricted Boltzmann machine, where these are real and these are binary stochastic. Then once you've learned this model on unlabeled data, you can think of copying these vectors of activity over there, treating that as training data, and learning another model. Then you copy it over, learn another model. Once you've learned all these models, you now want to combine them into one big model that's going to be a generative model of the data. In other words, it's still just a model of what the inputs look like. And what I mean by that is, with this generative model, if you were to generate from the model, you would get things that look like the data. And the way you would generate from this big model, which is very surprising, is you would take the top two layers and go backwards and forwards forever. And then you would, after going backwards and forwards forever here, you would just go chunk, chunk. In other words, these are directed top-down connections, but these are symmetric connections. And that's a huge surprise, because you'd think that if you put a bunch of symmetric things together like this, then you would get a great big Boltzmann machine. But you don't. You can go and read the papers about why you don't. I'm not going to try and explain it now. I've explained this many, many times, and I've never convinced anybody. So, read the papers. That is what you get. And so what we know how to do now is we know how to take data, learn features one layer at a time without knowing any labels, then put it all together into a great big generative model that has multiple layers of features and is a better generative model than just the lowest level ones alone. And once we've done all that, we can then say, now let's throw all the theory away, and let's just, instead of using the weight matrices this way, let's use them in the reverse direction, and let's treat it as a great big neural net. And we'll just put some class labels on top. We'll use what we learned here to initialize the weights, and then we'll use the backpropagation algorithm to train that thing. And the big difference from previous uses of backpropagation is that we used unlabeled data to initialize all our feature detectors. So the problem of feature discovery has been solved on unlabeled data. You found good feature detectors and multiple layers of them. And so in the higher layers, you've got quite complicated feature detectors, all found without using any labeled data. If you've only got a small amount of labeled data, you now turn backpropagation loose in that net and train it up, and it will work much better than if you, with that small amount of labeled data, tried to train the whole net. Because the labeled data is just slightly changing the features you found unsupervised. It's not having to design the features. However, the unfortunate thing about the story is if you've got a lot of labeled data, you don't need all this stuff. You just need to initialize the scales of the weights correctly. But we didn't discover that until we did all this stuff and discovered you could actually learn these deep nets. Until that point, people believed you just couldn't learn them, because they would initialize the weights wrong, and then it just wouldn't learn. After we'd done all this, just before we sent the paper off, I got the student to check, maybe if we just keep exploring all possible scales for the weights, it will learn. Because we had this wonderful graph where our system just learns beautifully, and if you initialize the weights at random, it doesn't learn anything at all. But then we explored all the scales for the weights, and we discovered this horrific thing, which is, if you get the scales just right, you can actually learn these deep nets quite well. Not as well as with the pre-training, but almost as well. And with enough labeled data, that can be good enough. So the reason why this generative pre-training makes sense is that you can train all these feature detectors, you can design your feature detectors on unlabeled data. After you put all these models together, you've got very simple inference. It's just a feed-forward net. It's doing approximate inference, but it's accurate approximate inference. And that means that you can take data, you can infer all your feature detectors much, much faster than you can if you use one of the normal directed graphical models, where you have a phenomenon called explaining away, which makes inference very complicated. So unfortunately, even though the pre-training makes it easier to optimize the net and reduces overfitting, now that we know how to initialize the weights, if you have a lot of labeled data, you can just initialize the weights to appropriate scales and then just train the backpropagation on the labeled data, and it works just fine. It will work a little bit better if you pre-train, but only a little bit. If, however, you don't have much labeled data, all this pre-training in a layer at a time is still very worth doing. So the first place this was used really successfully was in acoustic models of speech recognizers. And it was two students of mine, while I wasn't there, explored this technique for acoustic models. One was a very good speech student called Abdul Rahman Mohammed, and the other was a very good neural net and learning student called George Dahl. And they got it to work really well with a very deep net with 8 hidden layers. They then went off and did internships at IBM and Microsoft, and another student went to Google. And at those companies, they applied it to very big data sets and large vocabulary, and it worked really well. And now it's just replaced all that. At Google and Microsoft and IBM, they don't use their Gaussian mixture models anymore. They use these big deep nets because they work much better. And the reduction in word error rate is fairly dramatic. It's about a 30% reduction in the word error rate. That is, 30% of the errors disappear. There's a nice review paper on that, written by all 4 groups that were doing it. And what I want to talk about mainly today is what you have to do to take that success and also make it work for object recognition. And recognizing objects and images appears to be much tougher. It's a much bigger problem because in the acoustic model for speech, the acoustic model doesn't have to know that much. It's plausible that a few million connections could know enough about how to make bets about bits of phonemes from what's in the sound wave. There's not a huge amount of knowledge there. Whereas if you want something that will recognize objects and images in a sort of generic way, it needs to have a huge amount of knowledge about what objects look like. In the speech systems, that's in what's called the language model. And that we didn't touch, we just replaced the front end. So the computer vision community was pretty convinced that these deep neural nets would not be able to compete with their methods, even though their methods became progressively crummier over the years. They started off with very good methods, like what David Lowe did for his thesis, which kind of respected geometry and tried to recognize objects by finding a whole bunch of features that were consistently related to be part of that object. Sort of sensible things that took 3D geometry into account. And they ended up, because that didn't work as well as they hoped, they ended up falling back on the dumbest kind of machine learning, where you treat an image as just a bag of visual words and forget about their spatial relations, except that some of the words are over here and some of the words are over there. And it turned out that worked better. And instead of saying, well, I don't care that it works better, it's wrong, they said, okay, let's all switch to that. That was a big mistake, I believe. They all switched to that, and they said, that's the way to do it, and your deep neural nets are no good because we can do it better this way. And it turned out they could do it better because they had very small training sets. And all they had to do was take their hand-engineered features, actually take the features that David Lowe had hand-engineered, change them slightly so they had different names, and then tune a few parameters. And to do that, all you needed to do was have a small data set. But eventually they produced big data sets. And so they produced a data set with 1.2 million high-resolution training images. And the task is to identify 1,000 different object classes. Each image has been labeled. Now, the images contain several things, so you can't necessarily tell what label it's going to have. So the rules of the game are you get to give 5 bets. And if the label that a person associated with the image is in your top 5 bets, you win, otherwise you lose. And a bunch of computer vision teams competed at this, including some very good teams like Andrew Zisserman's group at Oxford and INRIO, which is the French National Research Labs, in collaboration with Xerox Europe. And if you look what results they got, then all the computer vision systems, these are good computer vision systems, were getting 26 or 27% or a little bit worse. And we were getting 16% on the same data, and if we used more data, we got 15%. And these guys couldn't use more data. But I've just done it on the same data set, we got 16%. So that's like a 10% gap, which is huge. It's a much bigger gap than we got initially with the speech stuff. So then we sold it to Google, and that's the end of the talk. Oh, I should carry on, should I? Okay. So here's some examples of things from the test set. And so if you look at this laser pointer has become. Does anybody have a laser pointer that works? Oh, that scared it. If you look there, you can see there's a motor scooter, but it's not the only thing in the image. There's lots of other stuff in the image. Now, the labels don't include labels for people, so you would normally attend to the people, but they're not labeled in these images. So, but it gets the motor scooter, right? You can't argue that this stuff is unable to deal with segmentation. I mean, it finds the motor scooter in there. Here, I would have said the right answer was sort of big rate convertible. The right answer is actually grill, and it gets that as its second answer. And the other answers it gets are pretty plausible. If you look at the last one, the stupid network says Dalmatian, when obviously the answer is cherry. The network does have a few other bets, like Staffordshire Bull Terrier, or grape, or elderberry, or currant. And if you think red currant, those look quite like red currants. But that's an example of the network getting something wrong. A judiciously chosen example of it getting something wrong. So the question is, how long will it be before this type of object recognition is actually in practical applications? And the answer is it went live last week. So if you go to Google+, you can upload your own photos, and you can search for terms. And there's quite a few terms you can search for. And it will find in your own untagged photos examples of those. I got these things from the web, so I couldn't leak anything. These are already on the web. So this is a search in somebody's photo collection for jewellery. And everything there is actually jewellery, including the motorbike, which is obviously a motorbike made of little jewels. And the one on the right is for snake, and they're all snakes. And so it does work pretty well. And it's good enough, as Alan Mackler said, it's consumer level. I think that was meant to mean it was good. Now, there were a bunch of tricks required to get it to work. The first trick was to get Yann LeCun to work for 20 years to figure out how to get it to work. That was a very good trick. He figured out lots of things about how to make convolutional nets work better and better, and we used all of them. Another trick, which is standard, was to take the images and take a large patch that was most of the image, and then move this patch around so that we got to deal with translations by just translating the data. Now that's a really dumb thing to do, and it has to be wrong. It's almost as stupid as bags of visual words. You really want to deal with the effects of changes of viewpoint by understanding how viewpoint affects things, like they do in computer graphics. It's really dumb to think you can deal with viewpoint just by seeing things from all possible viewpoints. But that's what these nets do at present, and it works. And that just shows we're going to be able to make this work much better. Okay. Another trick was not to use the standard logistic neurons. So neural nets use neurons with a kind of logistic input-output nonlinearity. And most people just sort of learn that that's what neural networks use. I remember when we made that up, and so I know there was no good reason for it. So we tried other things. And Yann LeCun tried other things too. And in fact, one thing you can try is, what if we had a whole bunch of logistic units that all had the same incoming and outgoing weights, but had slightly different thresholds? So I'll come to that in a minute. So I'll explain that in a minute. And also we came up with a much better regularizer that allows you to use big hidden layers with far too many parameters and not overfit. So I'm going to explain rectified linear units and dropout. But first I just want to go over what convolutional nets are, because they're the most important thing here. The idea is that you have feature detectors that you're going to learn. They look at the input image, but for any given feature detector, you replicate it across the input image. So it has a kernel, a set of weights, and you apply those set of weights everywhere. So you're doing a convolution followed by a nonlinearity. So in the picture there, you see 3 copies of the same feature detector. So all the red weights have the same value, and all the green weights have the same value, and all the blue weights have the same value. And you actually have a bunch of different maps, each with a different kernel. And you can do that for several layers. There's other ingredients to convolutional neural nets, but that's the main one. I'm not going to describe the pooling because I don't believe that's the right thing to do, but it works. So that's convolutional nets. You can actually apply convolutional nets to speech. And I actually did that in the 80s, where we had little filters that looked over time, and you replicated the filters over time. Actually, it was just one filter that stood there and let the data go by. And that was called time delay neural nets. And that's actually where Jan got the idea of convolutional nets from. He generalized that to 2D. But it turned out that what I was doing was stupid. I was using filters in time, and in speech, it's much better off to use them in frequency. Because the time is taken care of by the hidden Markov models. They can deal with different onset times and different rates. But in frequency, you get the variation in where the formants are due to the variation in the vocal tract length. And doing convolution locally in frequency gives you a significant improvement in speech recognition. And some students in Canada figured that out. And IBM has shown that it works very well. So here's the rectified linear units. We take a logistic unit, and we take a whole bunch of them that have different biases. So you have a learned bias B, but you then have a bias of a bit less than that, B minus 0.5, B minus 1.5, B minus 2.5. And so you have a whole bunch of feature detectors with progressively higher thresholds, and they've all got the same incoming and outgoing weights. So the only question is how many of them will turn on when you give them some input. And if you look at how many of them turn on, then you're interested in the sum of the logistic over all these things with step biases. And that sum turns out to be almost identical to log of 1 plus e to the x, which is shown in the black curve there. The logistics are in the exponential family, and log of 1 plus e to the x isn't. But it turns out that if you take the limit of that sum and make it an integral, it is exactly log of 1 plus e to the x. So we know that log of 1 plus e to the x is behaving like a whole bunch of logistics, but it's more powerful than one logistic because it doesn't saturate at the top, and so it's got much bigger dynamic range. And having seen that, you say, well, do I really need to have the log and the x? Maybe I can just do max of the input and 0, and that works fine. It's not quite so justified. I mean, I like the derivation from logistic units, but in the end, throw the derivation away and just get on with it. And that learns much faster than the logistic units. It has a bit more capacity. And so most people doing these deep neural nets have switched to using these rectified linear units now. You might ask what kinds of units are coming next. People in Montreal have tried. The rectified linear unit is a linear unit or 0, whichever is larger. So you can generalize that to say, why don't we have a whole bunch of different linear units in a pool and just take whichever gives the biggest output? And that's an interesting nonlinearity. And they've shown that in some circumstances that works slightly better. I still don't know whether it's generally better or just sometimes better, but it's a sensible thing to do. I think that the fact that we used logistic units for many years and there's something simple that works much better, or significantly better, and the fact there's many variants of that work even better, what it strongly suggests to me is that we've been far too conservative in designing these nets, and we should think about all sorts of complicated functions, but sensible ones. And maybe we could even get some inspiration from the brain. So what we call layers in neural nets are actually cortical areas. And in each cortical area you have mini-columns, And these mini columns do quite complicated little computations before they send it on to the next area. And I think we might be much better off having neural nets where you go to the next level. At the next level, you do some quite complicated little computations that involve some recurrence and maybe takes a few iterations. And then you send that to the next level. As you can backpropagate through recurrent nets. So you can backpropagate through all this stuff. All backpropagation requires is that you have a module, and you know how if you send stuff in, stuff will later come out. So you have the forward function. You also know how if you send derivatives of the error function with respect to what comes out in the top, you can get derivatives of the error function with respect to what goes in at the bottom. That's all that's required for backpropagation. And we should be more ambitious in the kinds of modules we explore. Jan's been saying this for many years. So I think maybe we can get closer to cortical columns. And the kind of neural inspiration I like is when making it more like the brain makes it work better. There's lots of people who say, you know, you ought to make it like the brain, like Henry Markram, for example. He says, give me $1 billion and I'll make something like the brain. But he doesn't actually know how to make it work. He just knows how to make it more and more like the brain without actually working. And that seems to me not the right approach. What we should do is we should stick with things that actually work and try and make them more like the brain. And in particular, notice when making it more like the brain is helpful. There's not much point making it more like the brain if it just makes it work worse. Okay. So here's one thing we couldn't do until recently with neural nets. Anybody who enters one of these machine learning competitions knows that if you want to win the competition, you have to train lots of different models and average them. And the more different, the better. But this averaging of different models is a very effective way to avoid overfitting. It's basically a committee. In universities, it can avoid getting anything done at all. But in fact, economists know this now. When you know, a sensible economist wants to predict what will happen next in the economy, you get kind of 15 experts and you average what they say. And that's better than picking one expert at random. It's probably worse than picking the best expert, but you don't know who the best expert is. So until recently, the way to average many models was to use decision trees. This was a technology that came from Leo Breiman. A decision tree is very fast to fit to data, and it's very fast to use at test time. So we can afford to fit lots of them, and we can afford to run many of them at test time. A decision tree is a fairly weak model. It's not nearly as powerful as a neural network. But you can fit a lot quickly and you can run them at test time. So that's called random forests, and that works pretty well. And what we'd like to do is do the equivalent of random forests with neural nets. We'd like to fit a whole bunch of neural nets, and we'd like to average them together at test time. And the problem is it's too much computation. So if you take one of our nets, it takes a long time to train. It takes like a week on a GPU to train one of these nets. If it's a big one, the object recognition one. And at test time, you don't want to be running lots of these big nets. It's going to be very expensive. So it looks like you can't do this kind of model averaging with neural nets. But it turns out that's wrong. There's a very simple way to do something. There's a form of model averaging. Before I show you how to do it, I want to distinguish two kinds of model averaging. They both work just fine. They both have nice guarantees on Kullback-Leibler divergences. That is, they show that the average of the models does better than picking one model at random. The first is the most obvious way, which is simply to say, if I've got two models, A and B, and I've got, say, 3 classes, I just average the probability distributions predicted by each model. So when we combine the models, we just average their output probabilities. The second is to take the geometric mean of the output probabilities. You just multiply them together. Now when you do that, you get some numbers that don't add up to 1 anymore. So you have to renormalize them by dividing by the sum. There's some important differences between these two ways of averaging models. In the first method, for example, the average model is always vaguer than the individual models. The average model can never be more precise than the most precise of the individual models. You have to get higher entropy this way. When you take a geometric mean, you can get either higher entropy or lower entropy. So in that sense, you might think it was more powerful. But anyway, this is just two ways of averaging. Now, I'm going to show you how to do this geometric averaging with neural nets very efficiently. What we do, let's take a neural net that has one hidden layer. Each time we showed a training example, we leave out half of the hidden units. So what we're doing is we're sampling from different model architectures. But the units we keep always have the same weights whenever we keep them. So you can think of it as, if we've got h hidden units, we've got 2 to the h possible architectures from which we're sampling at random. So most of them we never sample. But these architectures are doing massive amount of weight sharing. So only a few of these architectures get trained, one per training example. But this massive weight sharing is much better regularizer than things like L2 and L1, because the weights are being pulled not towards 0, but towards what other models would like them to be. They're being pulled towards sensible values. So it's not just shrinkage. And so having this huge set of, exponentially large set of models with all this weight sharing, turns out to work extremely well. One question is, what do we do at test time? Do we have to run exponentially many models? And here's a neat trick. At test time, what you do, instead of leaving out the units with a probability of a half, you just halve their outgoing weights. So you get the same expected value out, but with no variance at test time. And so you're using all the units, but each is only half as strong. And it turns out that does exactly compute the mean of all 2 to the h models. It computes the geometric mean. And so you sort of get it for free. So we just run one net at test time. It's twice as big as any of the individual nets we ran during training. And now we've computed the geometric mean. So this makes it possible to train a huge number of different models at training time efficiently, and to combine them at test time efficiently. If you have more hidden layers, you just keep doing dropout. You leave out 50%. You leave out 50% of the units in every layer.
You can switch on that. Switch on that.
Hello? Hello? Yeah. Okay. You leave out 50% of the units in every layer. And then at test time, you halve all the outgoing units. It's not exactly the same as computing the geometric mean of all the models anymore. But it's a close approximation, it works just fine. You can also leave out things in the input layer, and that helps too. That technique was already invented by Pascal Vincent and the University of Montreal and his collaborators. They got to it by a different route, but leaving out input, random inputs, also is a very good regularizer. People who know about machine learning are very familiar with that technique. If you compare naive Bayes with the logistic regression, in logistic regression you use all of the inputs to predict the output. In naive Bayes you leave out all but one of them. And it turns out if you don't have much data, it's better to train by leaving out all but one of them and train a whole bunch of different models and then average them. That's why so in naive Bayes is a very simple form of dropout on the inputs. So dropout works very well. And it'll reduce the errors by a whole lot on most neural nets if they're overfitting. If they're not overfitting, you should just be using a bigger neural net. However much data you have, I keep explaining this to Google, however much data you have, you can always use a neural net such that it will overfit. And that's what you should do. And then you should regularize it. And if you look at the regime people are in, statisticians live in a regime where your primary regularizer is the fact you don't have enough parameters. So the sort of default for a statistician is to have 1,000 training examples and 50 parameters. And then they're sort of happy, that's familiar. If you say, what about having 1,000 training examples and 1,000,000 parameters? They say, don't be stupid. But with dropout, you can do that. And if you think, what do people do? Well, people, you live for 10 to the 9 seconds. So let's suppose you had 10 training examples per second. That's not exactly a good model of video, but it'll do for now. You get 10 to the 10 training examples. But you have 10 to the 14 or 10 to the 15 parameters. So you've got 10,000 or 100,000 parameters per training example. So we're in the regime of massively more parameters than training examples. And that's because synapses are massively cheaper than experiences. A second of experience costs a lot of energy, whereas a synapse costs for a lifetime costs almost nothing compared with that. So we're in a totally different regime from statisticians. Another way to think about dropout is that it's like sex. There's this puzzle in sexual reproduction, which is you get all these nicely co-adapted genes, you then mate with somebody, and you produce an offspring, and half your nicely co-adapted genes have disappeared. And that seems like a bad thing to do. It seems like you'd be better just cloning yourself. And indeed, if the environment didn't change at all, I think you'd be better just cloning yourself. But suppose that the environment might suddenly change. Then having a big set of co-adapted genes is a very bad idea. Because if the environment changes, they won't all work so well together. Whereas having lots of little sets of co-adapted genes is a much better idea. So for example, if you work for Al-Qaeda, it's much better to have lots of little conspiracies than one big conspiracy. Because at test time, conditions are likely to be different from at training time. And if you have lots of little conspiracies, some of them will still work. I am in Canada, right? Okay. So let me tell you a couple of other cases. How am I doing for time? Okay. Let me tell you a couple of other cases where we now have a recipe. And the recipe is have a deep net. Pre-train it if you don't have much labeled training data, but if you do have lots of labeled training data, don't even bother. Initialize the weights to sensible values so that when you backpropagate the derivatives don't either die out or explode. Use rectified linear units. Use dropout to regularize it so that you can use many more parameters than you have training examples. And if it's got spatial structure in the data, use convolution at the front end. So that's our recipe, and that recipe will now solve all problems. So if you go to Kaggle, that's a place where they have machine learning competitions. And until recently, all the competitions were being won by amateurs, which should have been very embarrassing for machine learning professionals. The big machine learning groups didn't get involved in the competitions, even though there were serious financial prizes. And that's one reason was that random forests kept winning. Random forests do quite well on those competitions. But more recently, we've shown that our recipe beats random forests, and it does it fairly consistently. So one nice example is predicting the activity of a molecule from descriptors of the molecule. And so Merck set up a competition where you have about 11,000 descriptors of a molecule, and each particular task you have to do uses from 3 to 9,000 of those descriptors, but it's all drawn from the same pool of descriptors. And then you have to predict for the molecule whether it will bind well to something. And they've measured that for a whole bunch of molecules. But typically they've only measured it for a few thousand. So you've got a problem where the dimensionality of the input is about the same as the number of training examples. And George tried training standard backprop nets on this. And the problem is once you use more than 30 hidden units, the thing overfits terribly, even if you use strong L2 regularization. Because you've now got like 50 times more parameters than you have data points. But if you use dropout on this, you can use like 500 hidden units and multiple layers of them. So you can use hundreds of times more parameters than there are training examples. And it works really well. And the other thing that you can do is you can take many different tasks and train one net to solve all these problems. So the Merck competition, there's 15 targets, and you give them one set of molecules and ask how well do they bind to this target, and another set and ask how well do they bind to that target. And you just train out one big net to do it all. For the missing descriptors, you just treat those as dropout on the inputs. And it's really done. You just train the thing on a GPU. And if George trains it, it does really well because he's very good at training these things. And just that neural net would have won the competition. He actually averaged it with other things, but afterwards he went back and after he won, discovered that the neural net by itself would have won. Here's another one of those competitions. You're given the title of a job advertisement in England. You're given the body of the description, and you're given the location, and you have to predict the salary. And another of my students, Vladny, used exactly the same technology for that, and won it quite comfortably. And the person who came second was also using a neural net. So we now have a technology that at least can win these dumb competitions. Presumably, something else better is going to come along soon, but for now, it's good. I want to finish by talking a bit about speech recognition. So current speech recognition systems have a lot of different components. They have a language model which tries to predict the next word. And so if you can't hear it very well, the predictions will help. They have hidden Markov models to model the phonemes. They have an acoustic model to map from the coefficients you extract from the sound wave to probabilities of bits of the hidden Markov model. All of these are initially trained sort of separately, and then they're all put together. And if you want really good performance, you now try and train the whole thing together discriminatively at the end. But it's a big hodgepodge of different methods. And now that we've had some success, our imperialist inclinations are becoming clear. We would like to just do a whole speech system that's just one big recurrent neural net. That is, we would like to say the task is to get from a sound wave to a transcription. What's a transcription? It's just a sequence of characters with spaces included. And so what we want to do is take sound waves in here, characters out there, and the hell with all your technology, we're just going to train a great big neural net to do it. Now there's all sorts of reasons why you might believe that was hopeless, and one very good reason is the language model has to know a lot about words, and it has to be able to predict what word's coming next. And we're proposing to do that with something that just works at the character level, and that seems unreasonable. We're not going to have a separate pronunciation dictionary. We're going to learn all that. And we're not going to train it with forced alignment of the acoustic targets, which is what normal neural nets have done. So normally when you train these deep nets, you first train a dumb old-fashioned model that aligns the HMM with the input data, and then you use that to bootstrap your fancy neural net. It's like using an atom bomb to get an H-bomb going. You can't do an H-bomb without an atom bomb, I think. I hope Homeland Security is listening. Okay. So Alex Graves spent a lot of time working on this, and he already had the system that was best at reading online handwriting. And it's a recurrent net. And he developed it further by having a recurrent net that also has multiple hidden layers. So it's deep in time because it's recurrent, but it's also deep in space because it's got these multiple hidden layers. And on the TIMIT database, the best previous result was something like 18.9%. And they've now got it down to 18.7%. And that was after lots and lots of work. He got a lot better. 17.7% is a huge improvement, very unexpected. You can't go to his talk to learn the details, because that was at ICASP. But you could look it up on the web. So he has a paper at ICASP. Now on TIMIT, it's a small vocabulary. It's not big vocabulary. So you're avoiding the problem of having the recurrent net learn a language model. See, a language model is a bit like object recognition. A language model has to be a really good language model, it has to know everything you know. And that's a bit ambitious, but to be a fairly good language model, it still has to know a lot. It has to know about people's names, it has to know about places, it has to know about all sorts of funny foreign words. It seems implausible that you get a little recurrent net, or even a big recurrent net, working at the character level to model language. So I'm going to finish by showing you something that will make you think that's a bit less implausible. Ilya Sutskever trained a recurrent neural net that had about 8 million parameters in it, which isn't that many, to predict the next character in some text. And the text he took from Wikipedia. He got rid of all the really weird characters, like we got rid of all the French accents, which is a bit naughty. And he got it down to 86 characters, so sort of digits and letters, and capital letters and lowercase letters are different, and so on. And then he broke it up into 500 million characters from Wikipedia into 100 strings, 100 long. There's still 5 million of those. And then the recurrent net would see the first 11 characters and it would have to start predicting them. And he trains it just to predict the next character. There's some extra little tricks in how you do that I'm not going to go into. But this is basically a recurrent net with 8 million parameters that's trained to predict the next character. And the question is this insane? Because we know language is naturally made of words, or at least morphemes. And going down to the character level seems crazy. Although, of course, it's very good for agglutinative languages like Finnish, where words are made of 15 morphemes. You don't want to try and model words there. The amazing thing is it works very well. His recurrent net was about equal to the state of the art for character recognition, slightly worse. But it could do things like it could balance brackets 30 characters later. Because the recurrent net would remember, I've got an opening bracket and I better close it. In fact, if you gave it 2 opening brackets, it would get slightly worried and it would close one fairly quickly. The recurrent net we determined could count brackets. It could count none, 1, 2, or many. If you gave it 3 or more, it would close one very quickly. And it wouldn't necessarily close the right number. Okay, so he trained this on a GPU for a long time, and how well did it work? Well, the first question is, he's not telling it about words. So will it learn English words, or will it produce gobbledygook? So here's some text produced. And the way you produce text from the model is you give it some characters to get it going. You then say, give me the distribution for the next character. And if it says there's a probability of 1 in 100 that it's an X, then with a probability of 1 in 100, you sample an X, produce that as your output, and you tell the language model, the next character was an X, what do you predict next? And so it can progressively give you predictions. And so here's some text it produced. 1 character at a time. And the interesting thing is, there are no non-words here. And what that means is, as soon as it's produced enough of an English word, so there's only 1 completion, it never hypothesizes any of the inconsistent characters. Almost never. It does produce non-words, and the non-words are things like ephemerable or continged. So continged is not a word of English. But continged on knowing the network did it, it could be. Okay. So you'll notice this, it's got a sense of humour too. It likes the Irish intelligence agencies in the Mediterranean region. You'll notice it's got no coherence across sentences. But it's got a lot of syntax, it's got a lot of semantics. A lot of it's fairly shallow semantics. But it didn't have any problems learning what words were. And it didn't have any problems learning short-range syntax. So it really could, this recurrent net really could learn quite a good language model. Not quite as good as the whole word language models yet, but good enough to make you suspect that maybe we could put everything into one recurrent net. And so I'll conclude just by showing you that if you read 500 million characters from Wikipedia with no prior knowledge, that is, the prior knowledge consists of it's a neural net with 8 million connections and it does this, right? That's the prior. Oh, and that you're going to train it by gradient descent. And so here's a philosophical question for you. If that was your prior, and you saw a string of 500 million characters from Wikipedia, would you end up knowing the meaning of life? Okay. Now, it'd be pretty boring if you thought the meaning of life was 42, because that's in Wikipedia, right? It'd be much more interesting if you thought the meaning of life was something that you generated for yourself, having read Wikipedia. So here we go. Let's hope this works. Okay. What you do is you say the meaning of life is, and then you get it to carry on producing characters. It's a fun game. We were hoping it would say 42, and then we thought, that's a stupid hope, right? Because that's trivial. So, on the first version of the model we trained, which wasn't very good, on about the 3rd attempt, it said the meaning of life is literary recognition. I thought, boy, we've got it. Ilya then trained for another month, and we got a much better model. And he ran the model 10 times, and you run the model till you hit a full stop. And then we picked the best of the 10. Okay, so there's some selection, but there's only a few bits of selection here. And so here's how it completed the meaning of life is. So it's almost there. It's almost figured out the meaning of life. Okay. I'm done.
questions?
Yeah.
Is there a parallel between the initial unsupervised bit that you do and unsupervised dimensionality reduction?
Unsupervised?
Dimensionality reduction, like PCA. Like, is there some kind of parallel there?
Not much. That is, in many systems, you're going to try and reduce the dimensionality of the input because you don't want too many parameters or you don't want to do too much computation. And so PCA is throwing away information. Often, if you're lucky, that information is noise in the minor components. But typically, these nets work better if you expand the input. So for images, for example, the first hidden layer is going to be bigger than the number of pixels. And so it's not like we're going to try and get regularization by reducing dimensionality. You can use the same methods for reducing dimensionality, but that's not really the primary way it's working. Yeah?
So I know you don't know the answer to this, but I just wanted your best guess. Are these models similar to, let's say, the method used for cortical processing in the human brain, do you think? Or is there like a vast difference? And will we know the answer within the next 20 years?
I think there's about this much difference. I think we may well know the answer within the next 20 years. I think, now I've thought this consistently for a long time, but I think in the next 5 to 10 years, we're going to understand a lot more about how the brain is doing these kinds of computations. It better be in the next 10 years. And eventually we're going to understand how the brain does it. And that's going to be very exciting. It's going to help the technology. It may even help things like education. But it has to be doing it somehow. And it's pretty effective what the brain's doing. And as these techniques get better and better, it looks like a better and better bet for trying to understand what the brain's up to. And what I'd like to see is that we stay with the set of things that work and make them work better and better by making them more and more like the brain. And if we can do that, I think we will get to what the brain's actually up to. And I think we'll get there about 1,000 years quicker than Henry Markram. Yeah.
So I'm interested in the potential of generative models built up using unsupervised learning.
That's what I really believe in, by the way. All this discriminative trained stuff, it's just embarrassing that it works.
I really wish I knew if you were serious. But at any rate, so fairly far back in the presentation, you showed the initialization using unsupervised data, and you reached the point where we have a deep leaf net that's now running in the generative direction. I was wondering, do you think that is a good model for accomplishing, say, novel yet realistic generation? And what could you tell us about current research trends in that direction?
Yeah, I do. I think that's ultimately the way to go.
Okay.
But you let the results direct you. And right now we can make a lot of mileage out of the fact that discriminative methods are working very well. But for people, we don't get big labeled data sets. What we do get is we get big correlations in the input. You get words and objects, but they're just correlations in the input. So ultimately, I'm completely convinced that generative methods will be better, and that to do vision, you need to do inverse computer graphics. And you need to have a proper graphics model in there. And as soon as you do that, you'll be able to deal with viewpoint with no problems. That's the direction to go.
My question relates a little bit to that. So the models you present learn some form of abstraction or structure of the domain, however they do it. And of course, it's difficult to tease that structurally out of the network. Ultimately, if it really is learning, the correct abstractions, nouns and verbs, then you should be able to do things like one-shot learning. So if I say this is a floopy, then I shouldn't have to be like Google and have a lot of text that includes the word floopy in order to learn how to use that. And so you have any thoughts on how to do one-shot learning with this?
So it relates to the last question. If you can build good generative models, so you get internal representations that are, in a sense, that are what a computer graphics person would describe as correct. You know, they're the interesting parts of the object, and you have the spatial relation between those parts and other parts, or between those parts and the whole object. Then, from one shot, you're going to be able to see, oh, this is an object which has these familiar parts arranged in this new way. And, oh, there's another one in a completely different viewpoint, but it's the same parts arranged in the same way. I think that's the only hope for doing this one-shot generalization across big changes in viewpoint or lighting. And the way to do it is...
Do you see that being learned, or that being, first you inject it in a hand-engineered way, and then...
No, I see that being learned. But I think what you're going to inject in a hand-engineered way is, for example, the knowledge that coordinate transforms are linear operations. And so you can put in a big prior in this network saying, learn to handle this stuff with a sequence of linear operations. That's very, very strong constraint, because most things aren't linear operations. And it's completely insane that we're using these multiple layers of nonlinearities to deal with stuff that can be modeled, if you go to the right computer graphics representation, as linear operations. That's kind of insane. Because it's only linear things that you can extrapolate a long way. You're never going to extrapolate to totally different viewpoints unless you can find the linear manifold that everything lies on. And that's what we have to do.
So I guess what I'm hearing, Martin, is fair, but on the other hand, it's part of that is the point that you can maybe do experiments on the model and see disabling a certain part here or there with the effects, and also so what parts are important. So I'm kind of wondering if you have a network with millions of nodes or trillions of nodes, is it feasible to look at what those weights actually represent?
To some extent. I mean, the work done by Geoff Dean and Andrew Ng and Kwok Lee at Google on unsupervised learning from frames of YouTube videos, they showed that several layers into the network, using unsupervised learning, you will get neurons that really did represent cats. I mean, you could, if you multiply together the weights all the way down as if it were a linear system, which it isn't, then you can see the receptive field as cat-like. Or better, what you can do is you can take a neuron deep within the system, and you can take an input, and you can say, now let's keep changing the input in the direction to make this neuron happier and happier. And so you can optimize the input image for making this neuron fire. And then you can see what it likes most, at least what it likes most from where you started. And it's a cat. And it's a very convincing cat. And other ones are people. So you can do some work and find out what some of these internal things are doing. And it's very clear their big unsupervised net that had like 1 billion connections was learning to recognize familiar object classes. At least some of the neurons were doing that.
One last question. You've talked about nets that are both recurrent and non-recurrent, and I'm wondering, for the recurrent nets, were they also deep in the stacked direction, and is that important?
Okay, good question. So until fairly recently, we sort of said, well, if you ask what it means for a recurrent net to be deep in the stack direction, that's just some missing connections, right? If you have a hidden state and a full matrix connectivity to the next hidden state, then if you start leaving out blocks, then you get a layered system. So we thought, well, why not just go for the full one? It turns out that there's 2 reasons why not to just go for the full one when you're doing speech. One is that in order to get the speech recognition to work well in the recurrent net, Alex had to use nets in both directions, so it was offline. He would go forwards, and he would also go backwards. And he does that at each layer. So he goes forwards and backwards 4 different times in a 4-layer network. And that's spreading information around from the future and the past, and that's a big help. So actually layering it and doing a full forward-backward at each layer, not forward-backward in the HMM sense, but running a recurrent net in both directions, was a big help. That's what got him down from like 24% to 17.7%. So it turns out, and that was one of the innovations, layering these things.
Thank Professor Hinton one last